Good morning, everyone. You can see I had to reduce the size of my head so you can see as much of the PPT as possible. I will upload the PPT separately because my head, no matter how small it is, it's still going to block some things. So this is chapter 1.6, one of the easiest chapters. There's only a couple of things you need to know. But to be able to follow through this chapter, you should know the electron configuration. So specifically, you should know how it goes: 1s2, 2s2, 2p6, 3s2, 3p6, and so on. So just the first couple, as we explained in one of the previous chapters. So what is photoelectron spectroscopy? Well, it simply gives you a few pieces of information about whichever element we're working with. So the first piece of information this gives you is the number of energy sublevels. So this is 1s, this is 2s, this is 2p, and if we had another one, that would have been 3s. So they go in order. So the peaks here represent the sublevels. So one more time, we'll go 1s2, 2s2, 2p6, 3s2, 3p6, and so on. And the sizes of these peaks are simply the numbers correspond to the number of electrons in those sublevels. So look at this. This is the photoelectron spectrum of neon, as it says here. So 1s has 2 electrons. So the size of this corresponds to 2 electrons. And then 2s also has 2 electrons, so they're equal size. Now take a look at this. This is 3 times the size of this peak, which means logically that this has 6 electrons. It's important that you kind of learn how to compare the sizes of the peaks, because this information, they won't give you that in AP questions. They'll just give you the spectrum. They won't give you the number of electrons, and they won't even give you the sublevels. So you will have to know in which order they go. I just put a bunch of these examples here so you can kind of figure out how that works. The second piece of information that this gives you is the position of the peak. So if you look at here, you'll see it says binding energy. Again, this is not something that is going to be visible in most of the questions, but you should know whatever is more on the left side has a higher binding energy. This is logical. It's Coulomb's forces, right? So the electrons in 1s energy level are closer, 1s sublevel, are closer to the nucleus. So they're more attracted by the pluses. So they're more bound to the nucleus. So their binding energy is higher. And as you go to 2s, the binding energy gets lower. So it's kind of counterintuitive. So as you go right, the binding energy gets lower, not higher. And you have that explained really well here. So the bigger the nuclear charge of an atom, the more the peaks will move to the left side. They'll have a higher binding energy. For example, you will see examples later. I don't want to get into that right here. Of course, distance is what has most impacts. If you remember the Coulomb's law, with the distance, the attraction forces between plus and minus go way lower. So if the energy level is higher, right, and the energy sublevel is higher, there's going to be just weaker binding energy because of the weaker Coulomb forces, right? And then there is also this shielding. See, if we imagine we have 2 atoms or ions with the same number of protons, but one of them has higher number of electrons, then the electrons in the inner shell will shield the outer electrons from the influence of the nucleus. So the outer electrons will have a lower binding energy, will be moved to the right side. You will see, it's best to see how this works on an example. So let's do that right now. So take a look at this. A photoelectron spectrum of a neutral atom shows 4 peaks. What does that mean? That means this is 1s, 2s, 2p, and 3s, right? Again, in most AP questions, you won't have these, so you must know the electron configurations and how they go. So I know this is full, right? It must be full because only the last sublevel is not full, right? So this is 1s2, 2s2, 2p6, and this is obviously 3s2. Why? Because the size is equal to this. And again, the size corresponds to the number of electrons. So how will I find which atom this is? I can just add the electrons. You will see this later. So this is 2 plus 2 plus 2 plus 6. This has an atomic number of 12. So not only that I'm able to find that this is the electron configuration, I can also know which atom it is. And let's see. Yeah, I mean, you already have it in there. Now, the spectrum of the neutral atom shows peaks whose relative heights from highest to lowest binding energy are 2, 2, 6, 2, and 4. Identify the element. Again, same story. So I know this is 1s2, 2s2, 2p6, 3s2, and this is 3p4 because this is double the size of this, right? So I know that's the element. And I know it's sulfur because I can just add the electrons. So 2 plus 2 plus 6, that's 10. And then plus 2, 12. And then plus 4, 16. So the atomic number is 16. I can just go to the periodic table and find that it's sulfur. And again, it just confirms here. So atomic number 16. Now this one, predict the photoelectron spectrum of a neutral carbon atom. How many peaks in what order and with what relative heights? So carbon, you simply can just go to the periodic table and see that the carbon has the atomic number of 6, which means it's going to have 6 electrons. So you can then just fill in the configuration. It's going to be 1s2, right here, 2s2, 2p2, and then it's just going to look like this, right? Because this peak must be equal to this one. So as you can see, this is again pretty simple. Now this is an interesting one, and they love giving these in the AP questions. So 1s electron of lithium and of neon are both core electrons, yet neon's 1s peak appears at a much higher binding energy than lithium. Why? So these are the two 1s peaks. One is for lithium and one is for neon. And don't worry about the size. They didn't really, pay attention to that because this shouldn't look like this. But what they're asking for is why is neon more to the left compared to lithium? Why is this the case? Well, neon has more electrons in the nucleus, more protons, sorry, in the nucleus. So neon has more protons in the nucleus, which means that there is a higher plus charge in the nucleus. So that means that every electron of neon is pulled in more towards the nucleus and therefore will have a higher binding energy and it will be moved to the left side. So as you can see here, it tells us neon has 10 protons and lithium only has 3 protons. So it's much moved to the left side for neon. Yeah, more protons, stronger pull. And then you've got this. This is the shielding effect that we've been talking about. So magnesium atom, magnesium has 12 electrons, loses 2 electrons to become Mg2 plus. Describe how the spectrum of Mg2 plus, how is this different compared to this? So first of all, the most obvious difference will be that this will have 2 less electrons, right? So this is 1s2, 2s2, 2p6, and 3s2. But this one is missing. Mg2 plus is missing the last 2 electrons. So it's going to be 1s2, 2s2, 2p6. However, the remaining peaks, as it says here, stay in one place through all of them shift to the higher binding energy. What does that mean? Well, the fact that you have less electrons here means that the electrons are unable to shield each other as well as they shield each other here. You should think about shielding as like the nucleus has a positive charge. The more electrons there are outside, the more they're lowering the impact of the nucleus. So basically, all these peaks here will be moved slightly to the higher shift, to the left, to the higher binding energy. Sorry, not shift. So these will be moved a little bit to the left, to the higher binding energy, because there's less electrons, which means that there's less shielding effect. So the impact of the pluses to the minuses is bigger. Let me get this straight right now. So the shielding effect is the lowest possible impact. Everything else, the number of protons wins. The impact of the higher number of protons is much stronger than the shielding and not shielding. So the shielding is just when you have like this exactly the same number of protons but different number of electrons, then shielding has some impact. And here we have a bunch of smart explanations related to the question in the AP. So the taller of two peaks belongs to the electrons held more tightly. So that is a false statement. Why? Because the height of the peaks is just about the number of electrons. Doesn't mean anything else. So the height is just a number of the electrons. The peak at the highest binding energy is the 1s subshell. I mean, yeah, the closest the electron can get to the nucleus is 1s subshell. So yeah, that's the highest binding energy. Adding all the peak heights gives the atomic number. Yep, if we first determine which one is which number, so one is 2, the other one is 2, the third one is 4, and then you add them, you got 8. So yeah, adding the height of the peaks will help you determine the atomic number. And a peak twice as tall means those electrons need twice the energy to remove. So again, the height of the peaks is just about the number of the electrons. It has nothing to do with the binding energy. The binding energy is the position of that peak. So go and try a couple of questions. You can see this PPT by yourself. I'll leave it on the Forge, and let me know if you need any help. You can read the summary by yourself. I don't want to waste any more of your time. Good luck. See you soon.